Hi, welcome back for another 6 Caillou challenge. This is called Count the Divisible Numbers. Complete the function that takes 3 numbers x, y, and k, where x is less than or equal to y, and returns the number of integers within the range x to y, and that's an inclusive range. Both x and y are included in the set, that are divisible by k. And more scientifically speaking, they're saying you've got this set I such that I is between x and y, possibly equal to one of them or both of them, and I modulo k equals 0. Remember that the mod, it just means like the percent symbol that we've been using. It just means you perform a division, but instead of taking the quotient, you get the remainder instead. So hopefully that language is comfortable by now. Example, given x equals 6, y equals 11, and k equals 2, the function should return 3 because there are 3 numbers divisible by 2. So imagine if I wrote out 6, here I can do it over here, 6, 7, 8, 9, 10, 11, right? And remember 6 and 11 count, they said count the ends, and just see which ones divide by 2 evenly. 6 divided by 2, it's all the even numbers, right? So 6, 8, and 10. You can see there are 3 of them in this range here. And so you return 3. This note is important. The test cases are very large. I did confirm that. You'll need a big O of log n solution or better to pass. A constant time solution is possible. So you don't need to know about time complexity per se, but I will tell you that if you think you're going to use link and make an enumerable range, across x and y, and build this gigantic set of numbers and then sort of scan through them and modulo them to check, you're probably going to time out and run into trouble because the values get big. But if, part of learning is trying that. If you want to try that first just to see, go for it. So I think you have enough to get started. I think that's all the information you need. One thing I want to do is, I don't like X, Y, and Z. I think these are just horrendous names. I'm going to call mine min, max, and divisor, but use what you like. So yeah, go ahead, pause, come on back, and I'll go into a solution. Now, I'll do my normal sort of paranoid thing here. You don't have to do this part, but it's good practice to start thinking about your parameters and how you protect data. One thing that jumped out to me right away is, what if min and max aren't actually the min and max? What if max is min and min is max? So if you were worried about that, you could do a bit like if max is less than min. In other words, they just got passed in the wrong order, right? And believe me, it happens. People do that. Sometimes these parameters come as the result of mathematical calculations, that people, it's not clear. They think it's going to turn out one way, but it doesn't quite. So you see that all the time. And so you could say something like long temp equals max. You just store the max value because you're about to overwrite it. Set max to min, and you could say min equals temp, which was the original max value, right? And then you're sort of back in business. You don't have to do this, but I just like to get you thinking about what can happen and inspire you to sort of control your data and be the one in charge. This is your domain. Between these curly braces right here, this is your house. And you tell people, or you tell yourself, not in my house, and you enforce whatever rules you want in here, okay? Good. So I'll take that out. The challenge isn't going to throw you any tricks like that, but we're learning here that we're going to think that way. So good, we addressed that. So let me talk about the approach I want to do to solve this, to keep it reduced to pretty much some simple arithmetic. So my idea is going to be that I'm going to start at the minimum value, right? And I'm just going to kind of search forward until I find that value that divides cleanly in the range. And you can imagine I could go over the range and not find that, in which case I'll simply return 0, right? That's a nice, easy case to handle, right? You've went, using their example, let's say I went 6 through 11, I didn't find in a clean divide, so I just say, hey, there are no divisible counts, return 0. So we'll kind of start off like that, and then let's do that first, and then I'll take you a step further. So I'm going to create a local variable here. We're using longs. I'm just going to call it start, and it's going to be initialized to the minimum value. So in this case, 6, right? It's just like min there. And so I'm just going to kind of bump it up until I find a valid value, the first valid value in the range. So I can do something like, well, start modulo divisor is not equal to 0, right? That means we didn't find a clean divide. I'm just going to bump the value. So, right, I start at 6, it's going to go up to 7, then 8, then 9, that's all. And as an added measure, I'm going to say, we're going to cover that simple case. If I keep bumping start, right, imagine it goes past 11 and it gets to 12, 13. I'm going to say if start is greater than max, just return 0, right? That means you scanned the whole range and you didn't find anything. So done, simple, game over. So good. So now we have a starting point. And to illustrate, we already went through the example of this with 2, but let's consider some other values that will try to cover some other cases as well. So basically what I'm going to do is, provided, let's say I had a hit on 7, right? It divided out cleanly. I'm going to start here, and I'm going to basically get the number of elements that remain in the collection, and I can do that by subtracting, right? I can take the max value minus my starting point, and then you'll see I have to add 1 for counting purposes, right? Because if you do 11 minus 7, you get 4, but there's actually 1, 2, 3, 4, 5, right? So we'll get that range, and then I can simply divide by my divisor value. Like, let's say it was 7 here. Let's say k equals 7 here, right? And then what you would see then, right, is my clean divides would happen every 7, right? So 7, and the next one would be at 14, right? 13, 14, right? Let's say I only have up to 11, but you could see how they would repeat, right? It'd be 7, 14, 21, etc. So the idea is that I find whatever range I'm working with, and I divide it by 7, right? And then if there's a remainder, I know I have 1 in the range. So let's do some more coding, and we'll step through examples. So we're through there. That's good. So let's set that range. And the range, like I said, should be max minus start, and then we add 1 for the counting. Go ahead and plug in whatever numbers you want until you believe me. That's the number of values in question. Okay? So I'm going to check if there's a remainder when I divide the number of elements that I'm looking at, right? The range. Divisor. This, remember, modulo operator gives me the remainder, right? So I just called it remainder. And then the idea is that I can return range divided by divisor, right? And then I might have a couple extra slots, and we'll walk through some examples, so just hear me out. We'll say remainder is greater than 0. That means you have 1, right? And I'm saying add 1, else 0. And something like this should work, and let's consider it. So let's throw a few more. Well, let's keep 6 of 14. Let's try one like k equals 5, right? And so you can see in here clearly, right, there's going to be 1 in there. So our algorithm is going to start at the beginning at min. It's It's going to go up. 7 doesn't, 8 doesn't, 9 doesn't, 10. Oh, 10 divided by 5 is 2 evenly. So we found our start, right? Now we determine our range by subtracting 14 minus 10, right, which is 4, and we add 1. You can see I have highlighted 5 elements, right? And so the range is 5, and our remainder would be the range divided by the range modulo the divisor, which is 5. 5 modulo 5, if you take 5 divided by 5, it equals 1, and there's no remainder, so we have remainder 0. So again, range divided by divisor, instead of the remainder, it gives you the actual quotient, which we said was 1. 5 over 5 is 1. And because remainder is 0, it's not greater than 0, so we're adding 0. You're effectively not adding anything at all. And you're left with 1. And look at that. It worked out, right? We had 10, and we didn't quite get another one, right? We would have had to have our set go to 15 to get another one. But consider we had 15 then. The first hit would still be at 10, right? And then your new range is 10 to 15. 15 minus 10 is 5. You add 1, and we get the 6 elements that are visible there. And you'll see next time you come down, our range is 6. 6 divided by 5 is 1 with a remainder of 1. So now remainder is 1. That's the different part here. And range is 1 bigger. So range 6 divided by 5 is 1. Plus, since remainder is 1, that is greater than 0, you get an extra 1. And it bumped it up to 2 this time. And let's see, there should be 2 values in here, right? 1, 2, right? So that's good. That's the count that we wanted. And so you could do this with other examples, but I'm trying to show you how it works in general. Hopefully that's clear. But if you went out 20, right, then you'd hit again here. But if you stopped at 18, you know, it's not going to add anything. You still just have the 10 and the 15. And so your start's still 10, right? You've got 18 minus 10, which is 8, plus 1. You got 9 elements. So I called range 9. Range 9 divided by 5 would be 1 with a remainder of 4. 9 divided by 5 is 1. You get that remainder. So you still get 2, right? And you're not going to get that third one until this range over divisor bumps up to 2, right? When you get to 10, when your range hits 10. So when you get up to 20, you'll get that. So hopefully stepping through the example like that was clear, but if it's not, or you don't believe me this works in general, go ahead, make up your own values of k and try and convince yourself. You know, it's a great exercise. So before I even think that this is right, let's do some tests. Okay, good. Good. So yeah, it works in the general case as well. Now, one thing, cool if you thought of this while I was doing it, you might have said, hey bud, I noticed you add this part here, and you basically just said, if there's any kind of remainder, just go up. It's like rounding up, or hopefully you remember the ceiling function, right? If you have a partial value like 10.2, and you call a ceiling on it, you get 11, it just automatically rounds up. And so maybe you tried, or even in your own solution, right, you tried doing something like this and you were working with ceiling, and it's a problem because of how large the values are. So instead of doing this, let's demonstrate that. Let's use the ceiling function and see what we can get. So I'm gonna type this out a little bit differently. Let's comment this out. And we could say something like, I got to work with doubles because the ceiling, remember math ceiling, goes with double or decimal, right? Feel free to read the doc there. So double, call it quotient, and we'll say that equals to the range divided by the divisor. And I got to be careful, right? Because these are both integral values. So I'll just cast one to a double to make sure we don't lose any precision. Any of the fractional part doesn't get just cut off, right? So that's our quotient now. And then I'll say double ceiling can be the math ceiling of the quotient. Same kind of thing going on. And then finally we can return, return, we got to cast back to a long, right? The ceiling, right? And so we did the same kind of thing. Remember, range divided by divisor. And so the difference being is that we're doing double, so now we could have a fractional part to our answer, right? And then we're just saying, hey, we're push it up one if it's above 0. If it comes out exactly 0, then ceiling just gives you the same number. But you know, weird stuff with floating point, you can imagine if it's 0.000001, you know, or whatever. But let's run. Hopefully you can see how this is the same strategy, but instead of me making up my own kind of rounding thing here, we're using ceiling and now double precision numbers. So if I do this, I suspect we got to call, we didn't make up math, right? You got to bring in system. That's fair. Okay, so yeah, now you can see we're failing. You know what I mean? We're mostly right, but you know, these last couple values are off. We hit a lot that were still good, right? Maybe I could put in a print statement here to show what let's do that. Console right line, and we'll say quotient and ceiling I before E except after C, right? Okay. Sorry, this is an English class. All right, so yeah, still lots of good stuff, right? Mostly right. Lots of green there. Numbers aren't too big here, I guess. And then we get up here and check this out. Where we blew up, you can see the quotient. Look at, they can't even fit it all. You got the E plus 17, right? So you can imagine we're kind of losing some precision there, right? And so I think in theory this should work, but because of how large the values get with the long type, it just didn't work out in practice. So I'm going to go back to the original solution, but I wanted to bring that up in case you were trying to make this work and banging your head on the keyboard and all that. Yeah, I just avoided it because of the funny floating point shenanigans. So I'll go back, see if this was the right way. Yep, that's solid green. That looks good. I will remove my notes here. They're going to make me run again. But yeah, you can see it comes out to basically like a simple arithmetic once if you approach it the right way. And I'm sure somebody will have a much more clever answer than me. Again, if you want to refactor this right and look even cooler, you don't need to make range and remainder. Just plug these parts in where their names are used, right? I try to step this out for you guys so you can see what I'm doing, and I'm not just writing out one long line of blob text that you know looks intimidating, or it's not immediately clear what you're doing. I'm not cool, so I guess I won't refactor. I'll just leave it like this. Try to, maybe it helps someone else visualize the problem a little bit better who's looking through solutions like we do. So yeah, let's collect those points. Those are well earned. And yeah, there you go. You knew it was coming, right? So yeah, look through these. It's definitely some food for thought there, right? Otherwise, yeah, I'm sure some of you out there came up with some cool stuff too. Drop it in the comments. Uh, hit me up if there's any questions too. Otherwise, I think I'm going to make more challenges, solve more honor points. Thanks for watching.